I want you to picture yourself standing on a dock, just looking out at the water, and gliding past you is this massive, fully loaded cargo ship. I mean, it is an absolute mountain of steel.
Truly colossal.
Right. Stacked high with thousands of colorful shipping containers.
Hmm.
Or maybe it's sitting really low in the water, totally heavy, with thousands of tons of raw materials like coal or grain.
Yeah.
When you look at something that enormous, a structure that practically defies gravity and logic, you really have to wonder, how on earth does that thing not just tip right over?
It's a great question.
How does it stay perfectly balanced while carrying the equivalent of a small city across the most violent oceans on the planet?
Welcome to today's deep dive. I'm your host, and today we are going to look right through the steel hull of these modern leviathans.
And I'm your resident expert for today.
Yeah.
You know, it really is an illusion that these ships are just hollow metal bowls floating on the water.
Right. The reality is far more complex and honestly much more fascinating. To understand how global trade actually functions, you have to look at the hidden internal anatomy of these vessels. When you understand the engineering going on beneath the waterline, it completely changes the way you view the modern world and really everything we consume.
And that is exactly our mission today. We have a stack of highly detailed technical blueprints, maritime engineering specs, and structural data.
Really fascinating stuff in there.
Oh, absolutely.
Yeah.
And it is all focused on one incredibly vital source document we have today called 6balasttanks.pdf.
Yes.
Okay, let's unpack this. At first glance, a deep dive into maritime ballast systems might sound like the driest engineering topic you could possibly find.
It sounds a bit dense, sure.
Right, but the more I looked into our sources for this, the more I realized it is actually this brilliant high-stakes puzzle of physics and design.
Ballast tanks are essentially the unsung heroes of the high seas. They are these massive hidden compartments introduced at very specific strategic locations throughout a ship, and their entire purpose is to maintain the vessel's stability during a voyage.
Wow.
Without them, commercial shipping as we know it simply could not exist.
So I want to start with the basic physics of floating, because my initial assumption was always that a ship just needed to be shaped like a giant canoe to float properly.
A very common misconception.
Why would you want to intentionally pump heavy ocean water into a ship? Doesn't adding weight make it more likely to sink?
It sounds totally counterintuitive, I know, but ballasting isn't just about making the ship heavier, it is fundamentally about survival and control.
Okay.
There are 4 primary functions of a ballast system detailed in the specs, and the first one is actually about reducing the physical stress on the ship's hull.
Wait, how does adding thousands of tons of water reduce stress? I would think all that extra weight would just strain the metal even more.
Well, think about the sheer size of these vessels.
Yeah.
Some are a quarter of a mile long.
That is massive.
Right. So when you have a massive vessel riding over giant ocean swells, the middle of the ship might be supported by a wave while the front and back are just hanging in the air over the troughs.
Oh, I see.
Or conversely, the front and back are on waves and the middle is completely unsupported. The sheer weight of the steel alone can cause the entire hull to bend or warp.
Like bending a metal ruler.
Exactly. Engineers call this hogging and sagging. By intentionally pumping water into specific ballast tanks along the hull, you counteract those bending forces.
That is wild.
You are essentially using the weight of the ocean itself to hold the ship together.
You are using the ocean to fight the ocean. That is so cool. What about just keeping the ship upright, though?
Yes, that brings up the second function our sources highlight, which is transverse stability.
Transverse stability. I always picture this like being in a small kayak. If you lean too far over the left side of a kayak...
You flip immediately.
Exactly. To stay upright, you need your weight centered and balanced against the water. I assume a cargo ship is just dealing with that on a massive scale.
What's fascinating here is that we often think of a ship as a static object, a fixed shape moving from point A to point B.
Right.
But it is actually a highly dynamic system. It constantly needs its internal weight adjusted to interact safely with the ocean.
Because the cargo changes.
Precisely. If a massive container ship is carrying uneven cargo or getting slammed by sideways winds and waves, it uses ballast water to anchor its center of gravity.
Wow.
Every single time cargo is loaded onto the ship or unloaded at a port, the physics of that vessel completely change. The ballast system is what allows the ship to adapt to those changes in real time so it doesn't just roll over right there at the dock.
Okay, so we are keeping the ship from snapping in half, and we're keeping it from rolling over. But the sources also focus heavily on maneuverability, which I really didn't expect.
It is a crucial part of the design.
The third and fourth functions of these tanks are directly tied to steering and moving.
Absolutely. Think about an empty cargo ship. If it has unloaded all its containers, it rides incredibly high up on the water.
Like a cork.
Yeah. And if the ship is too high, the massive propeller at the back might actually lift right out of the ocean. Obviously, a giant propeller spinning in the empty air does absolutely nothing for forward momentum.
It's just splashing around.
Right. You have to intentionally weigh the back of the ship down to force the propeller to bite deep into the water.
And I'm guessing the fourth function is the exact same principle, but for the rudder.
You've got it. You cannot steer a quarter-mile-long vessel if your rudder isn't submerged deep enough in the water to create resistance.
That makes total sense.
So when you look at the big picture, the crew is balancing the structural integrity, the sideways roll of the vessel, the forward propulsion, and the directional steering.
All by moving liquid around inside the walls of the ship.
Yes.
Which perfectly transitions us into my next big question. If we are moving all this water around to steer and stay upright, where exactly is all this water hiding?
Good question.
Are all ships basically built the same way inside? Because I'm looking at these structural specs from the PDF, and a bulk carrier looks completely different from an oil tanker.
They are completely customized. Form follows function perfectly in maritime engineering.
Okay.
The specific location and shape of these ballast tanks is entirely dictated by the unique physical demands of what the ship is carrying. Let's look at bulk carriers first.
Those are the ships carrying loose, unpackaged cargo, like grain, coal, or iron ore. Right?
Exactly. The stuff you just pour directly into the hold. Because of that loose cargo, their internal cross-section is incredibly complex.
I'm looking at the diagram now.
At the very top corners of the hull, right under the deck, they have topside tanks. Then down at the bottom corners, they have what are called hopper tanks, which are angled inward.
Yeah, I see those.
And underneath the very floor of the cargo hold, they have double bottom, or DB tanks.
Why do they need tanks angled inward at the bottom corners, though? Wouldn't you want a flat square to maximize your cargo space?
If we connect this to the bigger picture, it's about unloading that cargo efficiently. A bulk carrier needs those angled hopper tanks at the bottom corners so that loose, granular cargo like wheat or coal naturally funnels toward the center of the hold.
Oh, it acts like a giant gravity-fed chute.
Exactly. If it were perfectly square, heavy machinery would have to be lowered in to scrape out all the corners.
That would be a nightmare.
And those topside tanks at the upper corners, they help raise the center of gravity just enough so the ship doesn't snap violently back and forth like a pendulum in the waves.
Which I assume can happen if heavy bulk cargo is sitting entirely at the bottom.
It absolutely can.
That makes total sense.
Mm.
Now contrast that with container ships and oil tankers. Based on the engineering diagrams we've been looking at, they don't have those angled hopper or topside tanks at all.
No, they don't.
Instead, they use completely vertical side tanks that run straight up the outer walls, paired with the double bottom tanks of the floor. It basically creates a giant, hollow, U-shaped protective shell around the entire cargo area.
That U-shape is crucial for entirely different reasons depending on the ship.
How so?
Well, for oil tankers, that double hull isn't just for ballast. It's actually a mandated environmental protection.
To prevent spills.
Right. If the outer hull gets punctured, the oil in the center hold doesn't immediately spill into the ocean.
Got it.
And for container ships, that vertical U-shape provides the massive structural rigidity needed to safely stack heavy, rigid steel boxes dozens of feet into the air without the ship twisting.
Wow. And then you have ro-ro ships, which stands for roll-on, roll-off.
Yes.
These are the weird-looking boxy ships that carry cars and trucks, literally driving them right onto the ship via ramps. Their cross-section seems to be the simplest of all. They rely primarily on just the double-bottom tanks beneath the cargo hold. No side tanks, no top tanks.
Cars are actually relatively light cargo compared to iron ore or crude oil. Yeah, relatively speaking. So they don't need the massive side ballasting systems. But regardless of whether you are looking at a bulk carrier, an oil tanker, or a car transport, all types of ships share two specific universal tanks.
Right, the bookends.
Exactly.
Right at the very back of the ship, surrounding the propeller shaft, is the aft peak tank. And right at the extremely pointy front of the bow is the forepeak tank.
Those two are universal because they allow the crew to adjust the trim of the vessel.
Which means dipping the nose up or down.
Correct. If you need the propeller deeper, you fill the aft peak. If you need the bow to cut through heavy freezing waves differently, you adjust the forepeak.
Here's where it gets really interesting. I want to take you inside that space we keep mentioning, the double bottom tank.
It's quite a space.
Because before I saw the specs for this, I just assumed the bottom of a ship was like a massive empty swimming pool beneath the floorboards. But it's not.
They're not at all.
If you were to actually climb down inside one of these tanks, you'd find yourself in a cramped, claustrophobic, incredibly complex structural grid.
Imagine the bottom of the ship isn't a hollow swimming pool, but an incredibly heavy-duty steel waffle iron, or a giant ice cube tray.
A steel waffle iron. I love that visual.
Those dividers are what engineers call girders and solid floors, and they act as the ship's skeleton.
Let's break down that physical architecture because it is intense. You have two main boundaries. The ceiling of this space is called the tank top, which is literally the floor of the cargo hold where the goods sit.
Right.
The floor of this space is the bottom plating, which is the actual exterior bottom of the ship touching the ocean. And separating the tank top and the bottom plating is this massive framework of steel.
Running straight down the center, acting as the main spine of the ship, is the continuous center girder.
Got it.
Flanking it on either side are the intercostal side girders. Then, running perpendicular to those, acting like the ribs of the ship, are the solid floors and bracket floors.
Wait, if the ship's bottom is filled with an intersecting grid of thick, heavy steel plates, doesn't all that extra metal make the ship terribly heavy and inefficient?
You would think so, but the genius of this design is in its duality and the specific cutouts engineers use.
Cutouts.
They don't just use solid slabs of steel, they cut large holes right in the middle of these plates, known as lightning holes.
Well, to make it lighter.
Exactly. They are cut out purely to save weight without sacrificing structural strength.
It reminds me of the honeycomb interior of an airplane wing.
It is the exact same engineering principle. This interlocking grid provides immense structural rigidity, preventing the ship from breaking its back in the waves.
But the empty spaces between all that steel, the pockets of our waffle iron, create incredibly safe, compartmentalized areas for holding thousands of tons of liquid ballast.
Precisely.
To give you a sense of human scale, one of the engineering files had a photograph taken inside one of these double-bottom tanks.
I know the one.
It shows a worker in a white jumpsuit crouching down inside this cramped, red-painted steel cavern holding a flashlight. He is completely surrounded by thick metal plates.
It's quite the image.
And the only way he got in there was through a manhole, which is just a heavy, black, oval-shaped hatch bolted onto the deck.
That really highlights the reality of maintaining these vessels. It is a harsh, confined environment. Everything is built from heavy steel to withstand enormous pressure.
Honestly, it made me shudder. So basically, they send someone with a flashlight into a tiny, pressurized steel honeycomb buried under thousands of tons of cargo at the bottom of the ocean. Suddenly, my desk job doesn't sound so bad.
I think anyone would agree with you there. But that level of human access is required because these tanks aren't just holding static water. Fluid dynamics are constantly at play.
Right.
Remember those structural steel plates acting like the ship's ribs? In addition to the large lightning holes in the center, they have smaller, highly specific holes cut into them.
I see them on the diagram.
Tucked up right against the ceiling, the tank top, are air holes. And right down against the bottom ocean plating, you have drain holes.
What are those for? Does the water need to move through the waffle iron?
Exactly. When the tank is being emptied, the water needs to actually flow through that entire grid of solid floors to reach the lowest point where the pumps are located.
Oh, I see.
The drain holes allow that lateral flow, and the air holes do the exact same thing for trapped air when the tank is filling up.
So the air escapes to the top, so you don't get massive pressurized air pockets trapped underneath the cargo floor.
Correct.
So what does this all mean? How do humans actually control thousands of tons of water inside this intricate, hidden maze?
The final section of our research dives into the crucial plumbing that makes the whole system breathe and drink.
It's a massive plumbing job.
And again, the scale of this is mind-blowing. There are pipelines, of course, massive tubes that carry the liquid in and out. But what really caught my eye was the bell mouth.
Ah, yes.
At the end of these pipelines, sitting just above the floor of the tank, the pipe flares out into a bell shape. It looks exactly like the end of a vacuum cleaner attachment.
That shape is incredibly deliberate. Think about trying to suck up a puddle of water with a regular straight straw.
Once the water gets low, the straight straw starts sucking in air, creating a vortex, and you lose suction before the puddle is actually gone.
Right, making that awful slurping noise.
Exactly. Now scale that up to industrial pumps trying to move 1,000 tons of water. If you just had a straight pipe, it would create a massive vortex, sucking in air and damaging the pumps before the tank was actually empty.
Oh, so the flared bell mouth spreads out the suction force.
It does. It allows the pumps to pull a smooth, continuous flow of water right down to the very last few inches. In maritime terms, that is called the stripping process.
Stripping process.
Yeah, getting the absolute last dregs of water out of a tank.
Okay, that makes sense. But then there was another component that confused me at first. The air vents.
Very important.
If you were building a waterproof tank designed to hold ocean water, why would you punch holes in the deck to let air in? I mean, to keep ocean waves from splashing down into the tanks, these air vents on the deck are shaped like massive candy canes.
Right, the pipe goes straight up and then hooks back down toward the floor.
Yeah. But why have them at all?
This is arguably one of the most critical safety features on the entire vessel. Imagine trying to suck the juice out of a juice box without letting any air back in. What happens to the box?
The sides immediately collapse inward.
Right. Now scale that up to a sealed steel compartment holding 1,000 tons of water. If you turn on massive industrial pumps to suck water out of a sealed ballast tank without an air vent to let atmospheric air in,
Don't tell me.
the negative pressure will literally crumple the heavy steel bulkheads inward like a tin can.
You're saying the pumps are strong enough to bend the structural hull of the ship.
Easily. And conversely, if you pump water into a sealed tank without letting the existing air out, the tank will overpressurize and could literally rupture or explode outward.
Wow.
The air vents protect the tanks from being underpressurized or overpressurized. They breathe the atmospheric air to equalize the pressure, while that candy cane shape physically blocks the crashing sea waves from getting in.
It's just incredible to think about the invisible forces at play.
Yeah.
But here is the most fascinating, beautifully simple part of this entire system.
The sounding method.
Yes.
Yeah.
How do you know how much water is actually inside a massive, dark steel tank buried at the bottom of the ship? With all this high-tech engineering, the solution is incredibly mechanical and physical. They use what is called the sounding method.
It is beautifully low tech.
It really is. They install a small-bore steel pipe called a sounding pipe that drops straight down from the deck all the way to the very bottom of the tank. A crew member takes a physical sounding tape, which looks like a heavy-duty weighted tape measure on a reel, and lowers it straight down the pipe.
All the way to the bottom.
It passes through the dark, hits the fluid surface, gets wet, and when they pull it back up, the water line on the tape gives them the exact depth or the sounding value.
It is basically the exact same way you check the oil in a car with a dipstick, just on a gargantuan scale.
This raises an important question, though, and it's a detail that really shows the foresight of maritime engineers.
Yes, the striker plate.
Consider the reality of this operation. You have crew members dropping heavy metal sounding tapes down these steel pipes day after day, year after year, for the entire 20 to 30 year lifespan of the cargo ship. Every single time that heavy metal tape hits the bottom, it strikes the steel.
Right on the hull.
Oh, wow. I didn't even think about that initially. If you repeatedly struck the bare bottom plating of the hull in the exact same spot over decades, you would eventually wear a dent or a weak spot right into the structural floor of the ship.
Exactly. You are inviting corrosion, stress fractures, and eventual failure of the hull. So directly beneath the open end of every sounding pipe, they weld a specific vital piece of metal called the striker plate.
Or datum plate.
Yes, it sits right on top of the bottom hull plating in that one specific spot. The striker plate exists specifically to take that repeated impact.
It is a small, replaceable piece of armor protecting the massive hull from the constant, repetitive act of simply measuring the water.
It is a perfect example of how every single detail in maritime engineering must account for both immense ocean-crushing forces and tiny, repetitive human actions.
It is absolutely brilliant. We started this deep dive by looking at a massive gravity-defying cargo ship, practically the size of a skyscraper.
And we ended up down at the very bottom.
Looking at a single replaceable plate of steel designed to take the tiny impact of a tape measure. It really puts the incredible unseen mechanical ballet happening beneath the waterline of every major vessel into perspective.
It really does.
The next time you receive a package in the mail, or buy imported coffee, or see a car that was manufactured overseas, take a moment to think about the complex system of bell mouths, inner bottom longitudinals, and sounding pipes that kept that cargo safe, upright, and stable in the high seas. You are relying on a vast hidden anatomy you never even see.
I think that leaves us with a fascinating thought to consider. If maintaining equilibrium on a single cargo ship requires such a vast, hidden, and constantly adjusting system of weights and counterweights, what other massive, invisible structures of ballast exist in our global supply chains, or even our daily lives?
Oh, that is great thought.
What are the stabilizing forces we completely rely on to keep our world from capsizing, even though we never see them functioning beneath the surface?
That is a brilliant question to end on. Thank you for joining us as we explored the hidden depths of global shipping. And until next time, keep looking beneath the surface.